Hi, everybody. Thanks for coming to our seminar and series of e-lightning presentations today. I'm Andy Miller. I organized the seminar. I'm just going to briefly um, put something up on the screen, just a moment to point out what's coming up next week, which is the last week for our seminar series this semester. So hopefully you can see this on the screen now. Um, Today is our annual JCET Geography and Environmental Systems poster session, and I'm going to turn it over to Ali Tokay to introduce the session and the speakers in just a moment. Our last seminar next Wednesday at this time will be presented by Dr. Akira Drake Rodriguez of the University of Pennsylvania, and her topic will be the topic of this book that she published earlier this year. It's about the politics of Atlanta's public housing. So it should be a really interesting presentation, and we look forward to having people join us for that. So I'm going to stop sharing, and I'm going to turn it over to Ali. And Ali, please take it away.
Hey,
You're on.
now let's see if am I sharing my screen?
Not yet. I may have booted you off, so you have to share again.
Okay, let me see if I can share it. Share.
Starting to share, yeah.
Okay, so all right, I just brought up again today's agenda here, and thanks so much again. I'm the Ali Tokay as a JCET faculty affiliated with the Geography and Environmental Systems. We are gonna have 7 presentations, and there are a couple purposes of this annual e-lightning or poster presentations in the past. Number one is the recognition the JCET faculty in the GES department. And number two is the opportunity of the summer internship with NASA and UMBC colleagues. So if you are interested about the summer internship opportunities, I strongly encourage you to contact us on this matter. All right, so our first speaker is gonna be Dr. Remer. So I'm gonna put her presentations on the screen, and then I will run her slides. Okay, Lorraine, I think you can go ahead. Thank you.
Thank you, Ali. So this is work I've been doing with, there's 5 of us in the group. We're looking at what happens to the ocean when atmospheric aerosols fall into the water. And we're looking at this from an ecosystem standpoint. The person who's done most of this work is Toby Westbury at Oregon State University, but it's been a really nice tight collaboration between atmospheric scientists and ocean scientists. In this image behind, which I think is a MODIS image, you can see the dust coming off of the Sahara, gets picked up by wind, transported over the ocean, and can make it from continent to continent. But the dust has to go someplace, right? And it falls into the water either by just settling or by getting involved in clouds and getting rained down into the water or on land. And we're going to try to ask the question is that how or if, mostly if, this material is falling into the water, what's going to happen to it? Okay, next slide, please. So these are 2 models, GEOS and MERA2. On the left, we have the average amount of dust that falls into the oceans. And it's done on the average on the left, and then the maximum, the biggest event of the year or the biggest event of the time series on the right. And you can see, even though the dust is mostly generated over the Sahara or the deserts of Asia, it has a wide range over most of the global ocean of falling into the water. And we're talking about tons and tons of material that goes into the water. And these are 2 models. You can see that they differ in how much they put into the water, but the patterns are very similar. So there's tons of material falling into the water that comes from the mineral elements of the land. Next slide, please. And this dust is full of stuff. It's full of phosphorus, full of iron, and all these other delicious nutrients that ecosystems could make use of in what they in production and making in their blooms and such. So phosphorus and iron are the two major nutrients that the dust contains, but it contains a lot of other stuff. And it's a complicated story because not only does the dust have to hold these minerals, it has to be bioavailable to the phytoplankton in the water for it to be absorbed by the phytoplankton to make more phytoplankton or to grow. And then there's critters that come along and graze on the phytoplankton. So it's a very complicated story, and I'm only going to give you a very tiny piece of it today because I only have 5 minutes. Next slide, please. So the oceans, this is another model, and this is a model showing what is limiting factor for phytoplankton growth in different areas. So if you see the blue area is phytoplankton that is limited by the amount of iron available to it. So if you add iron to these waters, phytoplankton then can have their bloom and multiply and process what they need to do. If you look at the green areas, that's phosphorus limited. That means that there's plenty of iron for the phytoplankton to grow, but there's not enough phosphorus. And there's other minerals too, there are limitations. And there's also limitations by light, limitations by temperature, and other things such as that. So this again is a model, and it's somewhat coarse. And then the 3 different panels are 3 different types of phytoplankton and what they're missing to encourage growth. So it is complicated. Some are missing iron, and some are missing phosphorus, and some are missing light. So it all depends. So now we have a question, is that if we, can we actually see, everything I've shown you so far is a model, but we can model the atmosphere very well. That's why weather forecasting has gotten so good. So we know where the dust is going and what falls into the water to some extent, but we're going to use satellite observations to determine what happens after an event. So we're looking at the biggest events in a 16-year time series, the top 10% of events globally. And we're going to look 4 days after that event to see if we see any changes in the phytoplankton. And we're using different parameters, but the most basic parameter is chlorophyll. Next slide, please. So to sum up, we see an increase in phytoplankton activity. So here are the deposits. We're looking at a 16-year record, and we're looking for a change in chlorophyll 4 days after the dust event. Next slide. So in the top panel, we're seeing what happens in the top 10% of dust deposition events. And if it's red, that means the chlorophyll has increased. If it's blue, it has decreased. And what's striking about this figure is that it's red almost everywhere. Not everywhere, because there's other things involved. But in general, 4 days after a big dust event, there's more chlorophyll. And if you look at the 10% sample that's randomly sampled, you get the bottom panel. So the difference between the top panel and the bottom panel is the statistical indication that the dust is making a difference, that the dust is feeding the phytoplankton and they are blooming. Next slide.
I think we are almost done.
And this is the first evidence. This is the last slide. This is the first evidence of atmospheric fertilization of the global oceans. First time. Okay, thank you.
Thank you so much, Lorraine. Appreciate it. Now let's move to our next speaker, Dr. Mehta. So, Amita, your slides are on the screen. Take it on, please.
Yes. Can you hear me?
Yes.
Yes, great. Thank you. Okay, so I want to show a small snippet of a long story. This is monitoring pre-fire risk areas and post-fire impacts in California. Next slide, please. So this is this was conducted, this training that Applied Remote Sensing training program conducted last year, focusing on monitoring fire, and it covered a number of aspects in the sense pre-fire weather and climate conditions, what are the vegetation conditions, fuel moisture content, and during and after, what kind of air quality impacts fires have in general. And then there were some case studies presented which showed about how to define fire risk area or how to look at post-fire impacts on water resources, vegetation, disasters, etc. And next, please. I am going to show just a small part of this, focusing on pre-fire conditions. How can we decide, can we quickly see how, where fires are more likely? And before I go in, I want to talk about Applied Remote Sensing Training Program, which did this training. That's a NASA Applied Sciences program, and we do online and in-person trainings tailored for, either people who are familiar with remote sensing or people who are not familiar with remote sensing. The idea is to disseminate information, so about NASA satellites, sensors, and data, and web-based tools which can help in decision-making in disasters management, health and air quality, land management, and water resources. And as you can see, in starting from 2009, a lot from global community has grown people who take these trainings. And so next, please. So I'm going to show a small part of this training. I'll talk about pre-fire climate and weather data analysis for California 2020 fire season, including precipitation, temperature, humidity, soil moisture, and a specific case of Bear Fire or Northern Complex Fire in California, which affected Feather River and Lake Oroville community. So here you can see already in the Western United States steadily a number of fires have gone up in last several years. And next, please. For 2020, if you see, there were fire frequencies already. There were like more than 8,000 fires covering large area of California. Next, please. So here is overall seasonal December, January, February, March, April, May, June, July, August, September, October, November. This is again a model-based 10-meter temperature. This is precipitation derived from global precipitation measurements and a number of other satellites. And this is also a land surface model which provides soil moisture in 0 to 10 centimeter. And what it shows, this is seasonal for California entirely. It's a wet and cold winters are there, warm and dry summers, and significant interannual variability in precipitation and corresponding soil moisture also. Next, please. If you look at spatial pattern, this is pre-fire season, so December, January, February, March, April, May. And so this is temperature. This is from MERA again. And here is the warmer temperatures almost everywhere, except for the northern part where it's slightly cooler. Next, please. This is for precipitation. Again, lower precipitation in southern California. The Central Valley and northern part has more rain. Of course, December, January, February, which is the main rainy season, that has more rain. So we're establishing what happens in pre-fire season, which is June, July, August. Next, please. And similarly, soil moisture, it shows that where more rain in northern part, there is more soil moisture and less in the southern part. Next, please. And these are the anomalies. So the previous one was average for 20 years, and this is just in departure from that average in 2020. So this is December, January, February. This is March, April, May. And the main main thing to see here are the anomalies. This is everywhere. The temperature is above normal. There are places here in northern part where precipitation and soil moisture are below normal in pre-fire seasons, both more in DJF. Next, please. If you combine that, this is what the picture you get. This is the warmer, the yellow part show warmer temperature anomalies and below normal precipitation and soil moisture. So this kind of helps you see that this particular fire season, this is the fire season. these are pre-seasons anomalies that can help you that, okay, looks like, and you can look at magnitude. This just shows the area where more fires are likely. Next, please. And if you see in August of 2020, this is where most fires occurred more in northern part, where you see warmer temperature anomalies and deficit of rainfall. Next, please. And if you look at the month of August, where we picked a fire, that bear fire, it occurred here. And this is again temperature from MERA, and this is relative humidity from MERA. This is now 3 hourly. What you can see is just before the fire began, you see even on like daily basis, slightly warmer temperature and corresponding relative humidity, of course, is lower. And once the fire occurs, then the winds pick up. These are the 3 hourly 1000 hectopascal winds. So this perhaps is a result of fire. Next, please. And this is the I-merge precipitation, although very small magnitude here. The fire started with lightning, and we just looked at precipitation. Does it show any signature? And you see this spike, although not much precipitation magnitude, but it does show that, okay, it's possible that there was lightning then. So we're trying to show that by using these NASA data from satellite and models, you can learn something about on climate scale, what's happening in pre-season, before fire season, and what weather conditions occurred before fire events. Next one.
I think we have to stop, Amita, because we got 16 minutes.
Okay, I just want to skip to the last slide. I just want to show, and the impact. Keep going, please, to the last one. Yeah, so this bear fire that affected Lake Oroville, you can see decrease in post-fire NDVI or vegetation. Next one. And this is the negative. Here is where the fire affected, where you see post-fire decrease in NDVI or vegetation burn. Next, please. And this is the downslope. So when rain occurs, and you can see the slides, when the rain occurs, decrease vegetation, increase runoff, and that affects water quality in Lake Oroville. Next, please. Yeah, next, I think I'll skip that. So the bottom line is that post-fire, next one. So once you have rainfall events and runoff increases, then next one, please. Yeah, so this is Lake Oroville. So this is pre-fire, and this is just after fire season. So this is more like in January 2021. Here you see a lot of sediments in Lake Oroville, resulting because there was a decrease in vegetation. And as soon as the rain started occurring, rainfall increased, and following so this is still it takes a few days, but then you see water quality affected by this. So the last one, thank you.
Thank you.
So for complete story, here's the website where you would see all aspects, atmosphere, land, and hydrology components related to pre-fire and post-fire impacts. But I just wanted to kind of give flavor that different data sets can provide a lot of information and potential for detailed research as well as application for decision making. So thank you.
Thank you, Amita. So I'm gonna move to our next speaker, Dr. Humerick is going to be our next speaker, and his slides are opening. And I think Fred is right on the screen. Take it on, please.
Okay, so what I want to talk about today is doing remote sensing from the space station. We're all used to seeing pictures of astronauts floating around in the space station and doing stuff with zero G, but the space station is actually also an interesting platform for advanced remote sensing studies. Next slide, please. So the space station itself is in kind of an odd orbit for remote sensing. Most of the work we do is from satellites like Landsat or MODIS or Sentinel, and those are all in polar orbits, whereas and sun synchronous polar orbits, which means they cover just about the entire Earth ultimately in their orbital paths, and they overpass places at the same time every day. Whereas the space station does not go that far north. It's inclined to 51 degrees, so it oscillates between 51 degrees north and south of the equator, and so it doesn't do high latitudes, and it's also not sun synchronous, so you get these observations at different times of the day. So that's both an opportunity and a challenge for using the remote sensing data if you're depending upon sun angle. The other thing about the space station that's important is that it provides a platform that can give, like, so you can send an instrument up there and the space station can provide power, communication, cooling. And so you don't need all of that stuff that you need to have an independent satellite. And the other thing about the space station is that because it has to be resupplied, there's regular flights to the space station. So it becomes fairly easy logistically to get an instrument from the ground into space. So this means the space station becomes a really interesting place to put new instruments on because you can do it relatively cheaply. Next slide, please. So what's end up, no, one back. So what's has ended up happening on the space station is a whole suite of instruments have ended up there, and these are like advanced instruments for doing new types of remote sensing studies. And at the moment, right now, there is JCET-GES, which is an imaging spectrometer that measures in the visible and near infrared. There's EcoStress, which is a multi-band thermal instrument, which is used for looking at transpiration and evaporation. There's Hisui, another type of imaging spectrometer that has more bands and goes out from the visible into the shortwave infrared. OCO3, which is an instrument designed for looking at the column CO2 in the atmosphere, but also can be used to measure chlorophyll fluorescence, which is an indicator of photosynthesis in plants, and JEDI, which is a LiDAR, which measures the tree height and surface topography. So what we have is a whole, and the thing that's interesting about these instruments is it's a really powerful suite. Next slide, please. That allows interactions that we can, combine these different data types to do interesting new research. And what I find interesting about this in terms of the space station is this wasn't a planned mission where NASA decided we want these instruments. Although if they'd come to me and asked, I would have asked for these instruments. Not that they would, but this opportunity occurs because the space station is a place that just kind of accumulated these instruments, each one having its own unique mission, but combined have really interesting potential. I'm going to talk now just really about using JCET data. We're working on a project that will use all of these instruments, but at the moment we've just started and we've gotten as far as using JCET data. So next slide, please. So what we're looking at is the productivity of forests. And one of the advantages of using the space station over using like aircraft data is that it gives us an opportunity to get repeat observations of the same site and allows us to look at widely distributed sites. And so in this study, we're looking at 3 different sites, one in out in the Pacific Northwest, that's a Douglas fir evergreen site, one in the Upper Peninsula of Michigan, which is a deciduous forest site, and one in Massachusetts, which is also a deciduous forest site. Next slide, please. All of these sites have flux towers on them, and their flux towers are a really powerful method that allows us to measure the CO2 transfer from the atmosphere into the ecosystem and from the ecosystem into the atmosphere. And so we can use the flux data to describe the productivity of a site by basically using the measurements of the amount of CO2 absorbed by the ecosystem through photosynthesis, and which is then the plant productivity. Next slide, please. So here's our three sites. In the upper three plots, the points are showing the, thank you. The points are showing the productivity, and you can see how for the conifer site, it's productive all through the year, although it does have some seasonal variation. But the really strong variation in the productivity of the deciduous sites. And the vertical lines are showing when we had DCES data. Next slide, please. So we tried a whole bunch of different ways of doing this to relate indices to productivity. One of the ones that works really well is looking at the derivative, which is something we can't do with data like from Landsat, multispectral data. We can use hyperspectral data to look at the curvature of the reflectance curve to get productivity. Next slide, please. And what we find is certain spectral regions, the curvature of the reflectance is strongly related to the productivity. And so showing ways that we can use this hyperspectral data that's not available through multispectral data, again, like Landsat, for looking at productivity of forest sites. And I'll quit there.
Thank you so much, Fred. And the next speaker is going to be Dr. Campbell. I'm opening her slides, and Pecha, you can take it over. Thank you. Go ahead.
Thank you for the introduction, and my presentation follows directly from the talk that you just heard from Dr. Humrick. And so I wanted to say how exciting it is now to be doing remote sensing, because we have all the old data collected by historical sensors and the new commercial sensors, hyperspectral, multispectral, we have time series. And so how can we use them together? What tools can we apply? And so we tested with this study how can we estimate a vegetation function using older historic data acquired with year one Hyperion and newer data from DCES. And Fred already introduced DCES, so you know about it. Next. Here, dataset 1 is the Hyperion dataset that covers the complete visible near-infrared and shortwave infrared region, while number 2 is the DCES data. And this is for agricultural site in Greenbelt, Maryland, which you may have seen when driving in Maryland. So then we can generated a convolved dataset combining the two. The Hyperion and the DCES, and so it is only covering the common region of 400 to 1000, and it is at the Hyperion 10 nanometer resolution, when the original resolution of DCES is 2.5 nanometers. So why all of this may be of interest to you? Next. In the spring, I will be teaching the GES 481 and 681 class, where you have a chance to work with such data, like the DCES, the Hyperion, or other commercial data samples will be provided for analysis, so you get experience. And so here we used a statistical approach, the partial least square regression approach to derive a model. And so it's a regression model for estimating GPP. And you can see how many components were used. And on the lower right corner is the equation itself. And this is with the Hyperion data, the complete WISWIR data set. So next. we used the convolved data set that includes all the data from the earlier and current time frames. And so it's much higher number of samples. And so you can see that less number of components were needed. This is though the visible near infrared data set. Nodes were regions, so you can see the equation, and the different regions were of importance. So the lesson is that using historical and new and the combined data sets, we will have to develop new statistical models, though we get better description of productivity if we have more data. Next. And also this way we were able to span the historic to current data time frame. So next we took a biophysical model, and this is the scope model. And so in the GES 481 class and 681, we will be talking about biophysical models. And so we use the spectra with the model to estimate traits such as canopy leaf area index or chlorophyll, and also GPP. Next. So these are the results using Hyperion, where we have had much more time because this is the historic data. And so we estimated the range in chlorophyll. This is the CAB parameter. CW is the water, dry matter, and others. Leaf area, it's LAI. And so also using the model, we used instantaneous PAR as at the time of the satellite acquisition, and derived a pretty good prediction of productivity, of canopy productivity. Next. We use the combined data set, Hyperion and DISES, and also derived the predictions of the canopy traits, and so chlorophyll level, water content, and so chlorophyll level was slightly higher, but with the similar range. And we're still working on the GPP predictions. So next. So we compared the traits derived with the historical data. So this is the and the convolved DESIS to Hyperion, and they were strongly correlated. However, comparing the convolved data sets to the very high resolution 2.5 nanometer data set, we found that there was overestimation of the lower values of dry matter, and leaf area index was predicted reasonably well, and the chlorophyll water content also, but there was a high variability. Next. So in conclusion, we learned with this simple example how to use together the historic and current data set and in time series with statistical and biophysical models. And we can estimate also canopy traits, which can be related, can be validated on the ground with real data. Also, the canopy photosynthetic function can be validated using tower observations, and they are also required for deriving the equations. And so, in conclusion, it is a very exciting time to be doing remote sensing. So I would like to encourage you to try the new data sets and merge them with the older ones. Thank you for your attention.
Thank you, Petya. So our next speaker is going to be Dr. Schumann, and slides are coming up. Okay, Christopher, go ahead. Thank you. Go ahead, Christopher.
The other button. Guys, because Mark can't be here, I put one of his early papers on the Northeast Greenland ice stream in the chat. But basically, this is a major ice flow feature, unlike any other in Greenland, very similar to some in West Antarctica. And the outflow goes through 3 outlets, and we're going to look at one of them as the ice shelf in front of the glacier collapses during the Landsat era. So Zachariah Eystrom is our focus, and Mark and I are still working on this for AGU presentation. Next slide. So Fred took us to the ISS. I'm going to take you to the very early version of the ISS, which is essentially long-range World War II era aircraft flying around the margins of Greenland and Antarctica taking pictures. So the picture on the left is a oblique aerial photograph of the area we're about to see through the Landsat era. The floating ice is the ice shelf. The glacier that is feeding that ice out of the interior of Greenland is the ice ström or ice stream. So between 1950 and 1975, we don't have a lot of looks at this area, but in 1975, you can see a good sized piece of East Greenland as the ice flows from the left of the image area out around the islands in the Greenland Sea. And basically, if you go to the next slide, you will see between 1975 and the beginning of 2002, there's not a lot of change. There's just slow flow. But then the sea ice off of Schnauder Island and Franski Islands breaks out late in the summer of 2002. The coverage is very partial, but we know that the thicker floating ice loses contact with Franski Islands, and that triggers what we see in the next slide, which is essentially the collapse of the Zachariah Eystrom ice shelf area. And by 2006, that has essentially separated the glacier's outflow from the Zachariah Eystrom ice shelf remnant. That is still a pretty sizable area, but it is basically no longer being supplied with ice from the interior of the Greenland. Jökulbugten is a perfect name for this bay. Jökull meaning from the Old Norse, broken ice. And the features in this area all have Danish attributes, which are kind of fun to try to pronounce. But what we're showing is the velocity evolution, and that's the work that's still ongoing. As we go to the next slide, you'll see that the transition from a stable position in the 70s, the 80s, through the 90s into the early 2000s, to the very rapidly retreating Zachariah Eystrom ice front. The calving of big icebergs is essentially a sign that that ice shelf is gone and it's not coming back. The area of 2,800 square kilometers is roughly the size of the entire urban area of Paris. It is a non-trivial ice loss. It was the largest remaining ice shelf in Greenland, and it is essentially a combination of warming from above, warming from below, and a gradual thinning of the glacier feeding ice out. If you cut off the supply, the ice shelf becomes unstable. And we will see where this story goes, because of course Zachariah does get deeper as it goes inland, much like some of the big outlets in Antarctica, and is already contributing a substantial amount to global sea level rise. So one more slide. This is literally meant to be a tribute to the colleagues that I've worked with at the USGS who saw the power of these images from Landsat and whatever sources were available to set the stage for the climate change that we are seeing today. So kudos to the USGS for their investments back in the day, and for the Landsat series, where those investments continue into the future. Thanks for your time.
Thanks so much, Christopher. So let's go to our next speaker. Dr. Turpie is our next speaker. The slides are opening up.
Yeah.
And
I'm also
Kevin?
putting in the chat a YouTube video if you're interested in looking at this later. Let's go to the first slide. All right. Thank you, Ali.
Sure.
So you might be wondering at this moment what the moon has to do with Earth observation from space. Well, I mean, obviously we're very interested in monitoring Earth systems from space, as presented in prior presentations. The instruments in orbit tend to change, especially in the harsh environment of space, and need to be frequently monitored and often recalibrated to remove spurious trends in our Earth observations. So the moon is a very stable reflector. It doesn't change like 1 part in 100 million or down as far as we can measure. And it can serve as a common absolute reference, a radiometric benchmark, if you will, to intercalibrate multiple Earth observing instruments in space, especially in support of satellite constellations. And it's also a stable climate-independent reference for multi-mission climate data time series, which is rather important if we're looking at the Earth over a long period of time. But to use the moon as a reference requires a model to predict the total lunar spectral radiance. Theoretically, as it changes phase, we can predict the moon's radiometric output to within 1 part in 1,000. But the current model to do that is called Rollo, originally developed by the USGS, has biases and requires new, highly accurate, SI traceable lunar measurements to improve its accuracy. Such measurements can also help with addressing large uncertainties that are associated with orbiting scanning measurements of the moon that we've noticed. So what does Air-Lucy have to offer to this? So Air-Lucy is an airborne spectrometer that measures from above 95% of the atmosphere, about well over 21 kilometers or 70,000 feet in altitude. This helps reduce the uncertainty by taking the atmosphere out of the equation. Our total target uncertainty is less than 0.5% ideally, and this is what we're working towards. Air-Lucy calibrates before and after we do our flights, and after campaigns, and we use sources from our National Institute of Standards and Technology, or NIST, and all our measurements are tied to international standards. Air-Lucy is operationally ready for making these fiduciary measurements of lunar spectral radiance. It's only high altitude NASA system for lunar characterization that is returned to the ground between measurements. There are future ones that will probably go up into space, but this greatly reduces risks. In general, the Air-Lucy philosophy is to provide open source data processing for our product, make every step of our measurement development and error estimation transparent, allow full vetting by the community. We were trying to make extremely accurate measurements and make them, or make a great deal of confidence in them. We also hold the ability to repeatedly recover and evaluate the instrument, as I mentioned, and it helps us learn about and improve the measurement process through discovery, characterization, and correction of small instrument anomalies and various types of errors. So back in November 2019, as a demonstration, we acquired data on 5 nights covering lunar phase angles from 10 to 60 degrees. That's near full out to a waxing moon. Our best effort error budget is currently below % for most of the visible to near infrared range, and we're wrapping up our characterization of uncertainty. And based on what we learned from our demonstration flights, we expect to reach our target uncertainties during our next campaign, which is planned in March of 2022. Next slide. So I'd like to share 4 plots were presented by Tom Stone at the 2021 CalCom meeting based on that data. And the first plot here, you see the lunar spectral radiance derived from our measurements. The phase angles, as mentioned, is going from 10 to 60 degrees, and they produce an absolute radiance range that spans a factor of 3 to 3.7. Next slide. So the second plot shows the Air-Lucy lunar radiance from the phase angle about 10 degrees. That's the one closest to a full moon. And it's the blue curve you see there. And then we have the TSIS-1 HSRS solar spectrum. This is the most recent estimate of the total solar output. And then we take the ratio of these to get a spectral albedo of the moon. And that's the green curve that you see here. And what you end up with is an extremely smooth curve. And this is what we expect to see from the moon. And this really is a very strong validation. Okay, Fraunhofer lines have been removed. Next slide. So the third plot here shows the comparison of these Air-Lucy reflectances against what's predicted by the Rollo model. And they are pretty consistently, characterizing a bias, which is what we are hoping to see. Next slide. So this first plot, shows basically with all the wavelength dependent biases removed, the difference between Rollo and Air-Lucy. And we see there's still some residual effects here that are probably due to some atmospheric effects that actually were built into Rollo since it's actually developed from the ground. Next slide. Okay, wrapping up, we will continue to do our first operational flight this March. The data collected then and subsequent campaigns will be used to improve the Rollo model, and this will provide synergy with other efforts with different approaches to characterize the neurospectral irradiance by providing an important validation resource. All right, that's it.
Thank you so much, Kevin. All right, so I will be the last speaker. So let me open up my slides and try to summarize. So today I'm going to talk about that my last summer's summer student intern is the Catherine Patch, came from University of Alabama in Huntsville. She was a rising senior. So let me tell you what she has been done working on the 10 weeks program virtually. So the title, of course, we are talking about today is the radar-based snowfall estimation and which reflectivity snow-water equivalent relationship we should use. So I have a movie that gives us a motivation that is coming from the NASA's Global Precipitation Measurement Mission that gives you the global mapping of the precipitation. And this is the one of the most used product. Now we are under the grant validation program of it. Satellites can give you a good estimate of precipitation, but at the grant we have a validation effort utilizing that our in situ instrumentations like gauges and distrometers or remote sensing instrument like a scanning and vertical pointing radars. So what Kathleen was trying to do, utilize this existing network we had in the Marquette, Michigan, which is on the shore of the Lake Superior, and which for a given event, which is the radar reflectivity snow water equivalent rate relationship they should use. Obviously, this location was choosing in purpose. As you can see here, for the winter of interest, she worked the data, it got over 200 inches of falling snow. So the site is about 13 kilometers inland from the lake and is a graduate slope about 200 meters. And I just put the green circle here where the measurements are taken, and you are seeing the operational ground radar circles of the 10 and 20 kilometers. Instrumentation that Catherine used over the summer primarily was something that we developed at NASA. The name is Precipitation Imaging Package. Reality, it's the only instrument that measures the size, fall velocity, and concentration of falling snowflakes. We don't have any other instruments at this scale. She also used a couple of other existing instrumentation, like you see in the picture, the MRR. This is very built by the Germans, micro rain radar, upward pointing K-band radar. And she also used the National Weather Service weather station located at the center to get to some environmental variables like temperature, humidity, and the wind. Methodology-wise, this is the equation. That is basically Z is the reflectivity, S is the snow water equivalent rate, A is the coefficient, and B is the exponent. Now, a couple fun facts are there. There are actually, if you look at the literature, much less relationships that you are going to find between the reflectivity and snow water equivalent rate versus the reflectivity versus rain rate. So there are much more studies done with the rain than the snow. However, if you look at the range of the coefficient and exponent, is much wider. So that means much more variability we have been seeing in the snow than in the rain. To set the equations are actually that middle of my slide, how you set, because actually the reflectivity, what you measure from the radar, that's what you see every night when you look at the radar screen in the weather report on TV, and the snow water equivalent rate, that's what you extract. Now, this is the study that we've been done using this PIP instrument, Precipitation Imaging Package, and the couple figures on the side shows for a couple cases, how those variables can be directly measured and can be distributed, and then taking the methodology that I will not have too much explain here. I will rather gonna tell you to evaluate which relationship's gonna give us the best relationship. We are using the bias and mean absolute error. The folks that taken with me GS 311 should be familiar with these equations. They have actually done for rain in this semester. So operational relationships. The National Weather Service of the United States use about 6 different operational relationships based on the location. And in addition to actually 5, and I add any other 3 from overall across the world. And one of them is actually multi-radar, multi-sensor, which we call MRS relationship, actually used by the GPM, Global Precipitation Mission. This is our main purpose. Couple results. I have just 2 results to give you today. One of them is one of the nice uniform event. What you see on the screen right now is the x-axis is the time scale, and the y-axis is the snow water equivalent rate. The black curve, either pluses or the accumulative curve, is the observation. That's basically what PIP observed. Now, in the top diagram, if you look at it, the blue curve, which is nearly almost at the top, has been derived for this case using from the PIP ZES relationship. The second plot from the top is the same thing, but in this case, derived based on the phase of the snowfall. Like, is it graupel? Is it a dendrite? Is it a needle? Is it a wet snow or plate? The third slide from the top is the ZS relationships, in this case, derived based on the ecotop height. Based on the MRR data, the vertically pointing radar, we were able to classify low, moderate, or high ecotops. And the very last one is the derived by the estimated bulk density, the high, mid-range, and low density. Based on that, we derive the ZES and we apply on that. So for this case, if you look at my very last slide, you've been seeing what we call them one-to-one diagram. X-axis tells you the measured, the actual reference, the snow water equivalent rate. The y-axis that you are seeing is the estimate. Top 2 rows, those are the 8 different operational ZS relationships. As the idea is, you would like to get the minimum mean absolute error. So that must, you want to have all your observations are on those one-to-one line. That's your best estimate. For this particular event, turned out to be, I will say that the very first one has the lowest out of 8 in terms of the operational relationship, but it's still not the best estimate. It's about 26% off. And now, if you, for the relationship directly derived from this particular data set, gives you the best estimate. The reason behind that, this was a rather uniform case, and the other physical-based algorithms were pretty good, but not the best for this case. Now, this was just the one case, and the conclusion is that there are many cases that Catherine looked at over the summer and find out that the cases that more uniformity, that the event drives may be the best, but the case has been more multiple phases, like the event starts like with the wet snow and turns to dry snow cases, that then you might need those physical-based relationships because they offer a multiple ZS relationships. That's all what I'm going to talk about today. Thank you so much. All right, Andy, I think I'm going to stop sharing my screen and giving to you, and then you can take it over for the questions.
Okay, thanks, Ali. We have a couple minutes left, and if people want to stick around for a few minutes after that, we can do that. Can you hear me? I guess you can, yes. So we're going to open it up for questions and answers. There are not a lot of questions that are in the chat at the moment. If people have any, please type them. I see one that Christopher Schumann just asked to, oh no, he wasn't the question. He was just telling people what ground truth is. So I want to open up for questions. Ketchup, were you about to say something? No, I'm just looking at your picture. That's all. Do we have any questions people want to ask? I'm going to ask Ali a question just based on what he was just showing them. So you showed that there's a number of different relationships you could derive. They all have varying amounts of the mean error. And you also said having multiple factors considered helps in terms of achieving a better match. Is there a way to incorporate that into the model, given that I assume you had to have those actual measurements to characterize the different conditions for which relationship would apply? In other words, is there a way to combine, use those relationships operationally when you're not in a situation where you're actually collecting that ground truth data?
Yeah, so, you know, the radar estimate rainfall or snowfall, you know, those A coefficient and B exponent is highly variable. We all know that. And understandably, National Weather Service cannot use hundreds of relationships. They have to use only a few. The one of the obviously kind of a correcting factor, what we call them the gauge adjustment. So what the National Weather Service does, like for instance, Canadians are still using a single relationship for an entire country, and which is pretty good for a wet snow, but not any other type of snow. So what they are relying is that they say, hey, we have a very good maybe rain gauge network, or I should say the rain bucket snow gauge network. Whatever the radar estimate, we can able to adjust or like a change the value is the using the gauges. And this is actually what like there is a NOAA product called Stage 4, and Stage 4 is actually involves the human who makes the correction based on what radar says, utilizing the in situ data on the ground. And that's kind of a one way to do it. But from the beginning, we are also not gonna have in situ data every single location. So can we get the best? So we just find that the events that has a uniformity, maybe it's okay, but then the events that have, of course, multi-assets, like, start with the grapple, ends with the plate, you might need more physical-based relationships. Thank you.
Thank you. I see there was so there was a question, but from Ali, and she just said ignored because she figured out the answer. So we are at 1 o'clock. If there are any questions you want to ask before we break, feel free. You can actually just unmute yourself and ask a question if you want before we finish. Does anybody else want to ask a question? It's hard when you have 7 speakers in a row to have people track that and keep their questions in line. I'm going to thank all the speakers for a series of really interesting talks and you know, it's actually an achievement to get all of that content into one short hour. And we of course have preserved it in a recording. So as soon as we get that recording back, we will actually have it posted on the YouTube channel of the Center for Social Science Scholarship. But we'll send the link back to Ali, and if JCET wants to post it, on their
Sure, thank
website,
you.
You'll have the link for doing that.
Thank you.
So I'll remind everybody, we have our last seminar of the semester next Wednesday at noon with Dr. Akira Drake Rodriguez from University of Pennsylvania, and a flyer will be going out shortly with that information. I see a question here for Fred. So Sarah, do you want to unmute and ask Fred your question? You could be the last question.
Well, Sarah, in answer to your question,
Well, let's read the question. Sorry,
I should read the question. She asked that all of the study sites we had in our study are about the same latitude, and do we do that on purpose? And no, that was really just kind of a coincidence. But the other factor in that is that sites that are more northern tend to get more overpasses of the space station, so you tend to get more data out of those by the nature of the odd orbit of the space station. So that's part of the reason.
Okay, thanks everybody for a great series of presentations. And we're going to stop the recording now. And we will